Welcome everybody, my name is Stefan from Keynote, and it's my pleasure to introduce you today to Oskar, who's going to give our keynote on the Wednesday. Just a short introduction of Oskar, and then you can start. He received his PhD in 2000 at Stanford University, and then he joined the Bell Labs at the Computer Science Center, where he was leading the steam computing effort. And then he founded in 2003 Maxeler, and at the same time he was also a consulting professor at the geophysics at Stanford University, and he was also heading the computer architecture group at the Imperial College. Recently, in 2012, he received an award from Consult that, with the title that Revolutionizing the World of Computers. So I'll give you the floor, Oskar.
Well, thank you very much for coming here at this early time. How does this work? This is going to be close to... Do you hear me just like this? I think this is much easier and I can just walk around. Excellent. So yes, thank you for being here at this very early time of this beautiful island. I know there's lots of other possible places where one can be out on the beach or staying out late, but it is impressive to see such a large assembly at 8:30 in the morning. So I'll try my best to kick off today with as much interesting stuff as possible. There may be things that you will agree with, things that you will dislike, things that you might like. So I'll try to have a very broad range of emotional material here, and so we'll see how that goes. Feel free to also interrupt and just barge in and ask questions or ask at the end any way that you like. So my talk here is about already the first controversial topic, which is maximum performance computing, which is trying to figure out what the fastest way is that we can compute within a certain amount of space or within a certain amount of power budget. And so that's already a goal that a lot of people disagree with. But anyway, that's my goal. I've had it now for a good 30 years when I started thinking about how I could get to build really large, big, powerful computers when I was 10 years old. And so this is kind of still my goal here, to try to squeeze as much out of computing technology as we possibly can in a particular place. So here's a motivating example that we ran across maybe 6-7 years ago. This is an imaging system. So what people do is they're trying to image the Earth under the sea, which by itself is already quite a large endeavor. And in order to do that, there is boats. Each one of these boats may have 1 or 2 helicopter landing pads. So these are fairly large boats. There are cables behind the boats. These cables are 10 kilometers long. So when this thing is moving across the ocean, it's the largest moving object on Earth. And in fact, you can, I was told, I haven't checked myself, but I was told you could actually see it from space, because it's 10 kilometers, and then as it's moving, it actually gives you a little shadow there. So you can imagine imaging underground there is a tremendous problem. And there is gigabytes of data every few seconds generated on each one of these vessels. Each one of these vessels have an actual data center stuck inside of them. As they're processing the data, they're basically doing an MRI of the Earth. And you can see this is a real motivating example for saying there's a finite amount of space and there's a finite amount of energy on this boat, clearly, because at some point, you run out of space on the boat, and also you need to generate the energy for all kinds of things, including the computer. So, given a limited amount of space, what is the maximum amount of computation that we can do? So here is a slide with a few challenges for the field and for the activity in general. So if you look at my list here, this is kind of an ad hoc list, so you have to bear with me a little bit on the detail here. But there are things like efficiency. How efficient is the computation that we're trying to do? What do we do about the microprocessors and the challenge that we are facing with microprocessors? And finally, what do we do with the challenge of parallel programming as it has evolved over the last few decades? And so what you're looking here is, well, first of all, on the efficiency side, I guess one of the questions, what is the maximum amount of computation per watt or per cubic foot or per cubic meter, depending on where you are? There is an exascale challenge. People are talking about the exascale, building computers for the exascale. And they're also talking about the fact that none of the standard vendors have any answer to how you're going to build an exascale computer anytime soon. So none of the current standard technologies are actually able to contemplate exascale computing, exaflops with exabytes of data. Of course, there's also operational costs. If one was able to build an exaflop computer, who's going to pay for the electricity? How are we going to get the space all together in one place? And how is it actually going to be managed? How many people would be needed? And how would you organize an activity around an exaflop? So there are several issues on the efficiency side. If you look at microprocessors, my first point really relates to some of the discussions that we've had yesterday as well, which is when I got started, the first conference I went to was the ISCA conference. It was the ISCA conference in Santa Margherita, Ligure, which was a grand conference in the middle of the 90s. It was 1995, just before the big boom of internet activities, a lot of excitement around that place. And in fact, the first lecture that I ever heard in computer architecture was Yale Pat giving a lecture just before, the day before, in one of the tutorials. And so that was the grand time of computer architecture. I have to say though, looking at what ISCA has produced, the cages that they have put around what is acceptable, what can be published, what is good computer architecture work, have really been more than stifling the field, rather than encouraging people to take risks, do novel things, and explore a wide range of activities. And then so that's one of the issues that I see with actually reaching the exascale, is if you keep doing the same thing, how are you going to accomplish something new? You have by now, back then of course you didn't, but by now you have a dominance of an Intel instruction set, which is a level of abstraction which puts another cage around the computer architecture. Whatever you do, it has to be useful for Intel, otherwise, you know, there is nothing else out there. And so if you are trying to think about how to run very large applications today, you are kind of limited to whatever is going to be useful for Intel, and you're limited to also doing research for Intel, because that's all there is. That's all that you're allowed to publish today. The next one is a little bit more fundamental to computation, which is that if you look at the 80s and 90s, there was still a lot of research around all kinds of different computing paradigms, all kinds of different models of execution, and that has all more or less died out. So we've basically accepted that there is one way of building computers, and we are not going to investigate any other ways anymore because we were told to do so. And so that's yet another challenge. If you think about the von Neumann architecture, when it first came out, it was a world where keeping 10 bytes in your computer was a major accomplishment. And disks were probably this large, this thick metal rings that were rotating, if at all. And then that was the preferred choice for an architecture at the time. And we are still today limiting ourselves to the same style of computation simply because of the amount of momentum and inertia that exists in an industry that has built a lot of things around that concept. Finally, even more contentious, now we're getting into the more contentious things here, IEEE floating point has been established, and nobody is allowed to add or multiply numbers any other way anymore, because that is the way that has been determined to be done. Which again stifles a lot of opportunities around finding new ways of doing things around arithmetic around adding, multiplying numbers, representing them. And it will become a little bit clearer later on what that means. And finally, of course, parallel programming. We all know parallel programming is hard. There is an interesting point that I would like to make before the whole thing starts here, which is, if you think about performance being limited by data movement, all the great ideas around Amdahl's law go out the window straight away. Because Amdahl's law talks about sections of code and which percentage of the sections of code you're talking about. Now, if your performance is limited by having to move the bit of data in and out, the entire thing doesn't work anymore. So, just to give you the motivating example again so you can see. So how do these nodes communicate, right, with a data center? Well, they have a communication port on top, as I mentioned. I don't know if you caught on that I was talking about the communication port, but the helicopter landing pads are the ways that data is being exchanged. And so you have helicopters, you have guys with disks in their hands, in suitcases, they run onto the helicopter, they fly over, and they have a communication port on the helicopter. And that's the way that data moves around. So performance may indeed be limited, at least in some cases, by moving the data. There's also people who claim that moving data around the chip is hard these days, but the consequence of that is really not very attractive. And so ignoring the consequences of moving the data on the chip and then off the chip again, because of course the pins are limited, that causes a lot of problems. David May, who I think was mentioned yesterday as well, had some interesting laws and statements that he makes over time. I particularly like the idea that compilers improve 2 times in 10 years or more, while at the same time, software efficiency halves every 18 months. And so as software is being developed, it just goes down in performance. And I don't know about the 18 months, but it is certainly an interesting statement to consider. Of course, while programming things that run in parallel is fairly difficult, actually reading programs that are highly optimized for parallel execution is almost impossible. Figuring out what the thing is doing is just way out there. And so that's where really the keynote of yesterday was really inspiring, to try to create a programming paradigm, something that expresses computation where the timing and the parallelism is a little bit more readable. So one of the things I wanted to show is a paper that I wrote as a student a long time ago. That was 1998. So I wrote this paper, and just like the keynote yesterday, I submitted it to the Wild and Crazy session. This was the Wild and Crazy session at ASCLOS. So this was the Wild and Crazy session, ASCLOS 1998. I was also told later on that was at the lunch, that self-promotion is a really bad thing. You're not supposed to talk about the publications and the papers that you're publishing. And luckily, this is a great example, because this paper didn't get published, it got rejected. So I'm completely fine on that front. This paper got rejected to the Wild and Crazy session in 1998, and it basically laid out exactly what we continued to do for the next 14 years after that. And that's what this talk is really about. So if your paper does get rejected somewhere, you should really consider 2 options. One is that it's a really bad idea, you should really throw it away and bin it. And the other option is that actually it may be a good idea because people don't like it. So, so this was here. So let's get back to the topic here, which is limits of computation. As a scientist, beyond actually trying to build a system, one of the fundamental questions here is, what is the limit on computation per cubic foot inside of a space? And the last really good work on this topic, if I'm honest, I have to say, goes back to Feynman. If you look at the lectures on computation, he was actually tackling the real problem. How much computation can you do for a particular amount of energy? And interestingly enough, he came out with a solution from a physics perspective. There is no use for spending energy on computation at all. Turns out you could compute an infinite amount of computation with no energy dissipation whatsoever, as long as you don't lose information. So the only thing that we actually pay for is reducing information. If we could only keep all the information around and rearrange it in a way that would create the result, that would be sufficient. And that wouldn't necessarily, from a physics perspective, require any energy to be dissipated at all. And then he left it at that, and that was kind of enough from a physics perspective. He's done the physics, it's all clear, there is no energy needed for computation. He's done with that topic. People followed up on that, and there was interesting work being done at MIT, which looked at transforming numbers, transforming inputs into outputs without losing any of the information. That work kind of led forward also in conjunction with some other people working on data flow, on thinking about data flowing through a system and being transformed as it flows through that system. So one of the key conjectures that I have here, and of course I don't have any solid proofs either way, but I have a few examples of where we might look. But the real conjecture is that data movement is the real limit of computation. It's about how we move the data and where it needs to go, which is the fundamental actual limit on how much we can do. So if we break that down kind of in a slightly simplistic way, you could say less data movement, which is what we want to do, we want to minimize the data movement. And so we can split that mathematically into less data and less movement. So in order to compute as fast as possible, you want to have...
I have a question. Why is not a product, less data, but a plus? This is a combination, so it should be a product and not a plus.
Well,
it means more. You just overloaded the
I think...
Okay, thank you for your answer.
Thank you for this.
No, so all of this work can clearly use a lot of improvement, and that's why I'm not just sitting there doing this, but coming out to tell you. So this is great. Yeah, I can see that. So what I'm interested in kind of mentioning, and this may be a little bit a wider range of topics than you might have expected from the title talk, but there is information theory connection. There is a connection to a recent Nobel Prize in economics by Daniel Kahneman, and then connects with, of course, the von Neumann architecture as well. And then we'll see some real data flow implications and actual machines that we have built that are running in production and that show what people are doing with these machines, how they work, and what we do with them. So if I start here with Kolmogorov, one of my favorites, of course you will argue that the right person to mention is Shannon, and he's the one who's invented all of the limits. But the corollary of that was really done by Kolmogorov, and it fits a little bit better with the spirit of what I'm trying to talk about. And the spirit there is that if a description of a string S is of minimal length, meaning we have the optimal description of that string, we call that the minimal description. The length of the S is the Kolmogorov complexity. The complexity of a piece of information is the smallest amount of bits that we need in order to communicate that information. And if data movement is indeed the problem. Minimizing the amount of data helps. And this is one way to do it. It's very unfortunate only that Kolmogorov didn't figure out how to do it. He just figured out that there is such a thing and we would like to have it. But really, there could be lots of methods and we don't have any optimal algorithm to do this. We can still strive to do it though, and so following Kolmogorov's spirit, we should do that. Unfortunately, there is yet another problem. Now, yes, there is a minimal description of that string and we can use the bits, but that's not enough, right? Because if you just have bits, they don't help you. You need a language. You need these bits to signify something in order for these bits to represent something. And so, yes, there is actually another problem, which is what's your language that you're using in order to describe these things. So there's plenty of opportunity to not just minimize the number of bits, look for the optimal representation, but also for each problem instance, for each activity that you're doing, think about what is the optimal language in order to do that. So it gets a little bit worse on this one. If we are looking at computation, we're looking at computing a particular function. You say, well, there's an input, there is a function, there is an output. Okay, so the task F is to compute R given I, and then there is a function F in the middle. So now, if we are assuming an infinite capacity to compute and remember inside of the box F. So let's say there is infinite memory inside box F. There is an infinite capacity to compute. Clearly, the time to compute the task depends on how much time we need in order to get I into the box and how much time we need to get the result out of the box. Right? So we're limited by the box state. So for a machine with infinite memory and infinitely fast arithmetic, the Kolmogorov complexity of the input plus the output really defines the fastest way to compute task F. And so this is motivated by the fact that you're limited by pins on the chip. Pins are there. How many more pins are you going to put there? Right? So there is an issue of getting data in and out of the chip. The amount of computation inside of the chip is growing radically. The amount of memory inside of the chip is growing. The pins are staying as a limitation. So in the limit of all of this, you get this kind of behavior. Jumping yet again very, very far away from where we've been on the previous slide, if you thought that the previous slides were far away. This is actual computation. So this is maybe 80%, 90% of scientific computations out there. It's a partial differential equation and a solving of that partial differential equation. It turns out most of physics and science in general today operates that way. And so one of my observations is that even though as computer scientists, we talk a lot about computation, can I just get a show of hands? How many people here have discretized the partial differential equation before? Small group. So this is really what I feel is one of the limiting factors in computation, which is taking into consideration the partial differential equation up there, going through a discretization step, figuring out what actually needs to be computed. So the step down there really leads to a Monte Carlo simulation where you do the iterations on the Monte Carlo thing. And what we've done going from the top to the middle is to discretize the computation in time and in space. What we are not talking about here, and what people like to ignore, is that we've also discretized the value. The variables here assume that you can take on any value that you want, but that's not true. Any of these variables is going to go into a computer, right? You're going to type this in into some programming language, and it's going to give you some kind of value. What is the discretization? Well, the discretization is your floating point number, right? Because that's what you're using. But you can change the type of this variable very easily, very quickly. Anybody can change the type. Thinking about what the discretization or the type of that variable really means compared to the discretization that we've done here, and what the relationship is between the length of this time step. So we go from t to t plus 1. How long is that? How much time is that in the real world? How much time should it be? How much time could it be? Does it depend maybe on the type of representation that we're using? So there is one more dimension in terms of discretization, which is in value, which is typically being ignored. There is another example down here, which is another way to look at this. And that should, of course, be the bread and butter of any computer scientist. It's a state machine. And you turn out, well, the state machine is the state machine for the computation up there. Okay? So then we say, well, what's the optimal way to compute that? What's the optimal way to compute in a state machine? Now we know that one. That is a problem that we have actually addressed in detail over the last 2 decades. A lot of people have spent their whole careers thinking about this, right? And we all know, well, clearly it depends on the state and the logic. But we know how to do logic minimization. We can crunch that down to as small activity as possible. So we are left with the state. Oh, but we're not allowed to touch the state. So on one side, we are taught that the optimal way to go through the state machine is to optimize the state of that state machine, to minimize the time to the logic, right? On the other hand, we are told that, well, you're only allowed to use IEEE floating point. You're not allowed to touch the state. The state is fixed. You're not, that's off limits. Not allowed to do that, because if you do that, well, you could actually make things go faster, which, yeah, that would create all kinds of problems. So by considering the discretization and value, you're actually changing the state, you're changing the time it takes to go through that stage. So in terms of getting back to getting at the maximum, getting the maximum performance out, the bad news, well, real computers do not have infinite memory or infinitely fast arithmetic units. But at the same time, we're getting there. They're improving, it's getting more and more, and so that should be fine. And the other problem, of course, is that the Kolmogorov's function k is not computable, so we don't really know how to do that. So a lot of thinking is required. A lot of actual research is required to figure out how to do such a thing. The good news on the maximum performance computing front is that today's arithmetic units are fairly fast, and so in practice, the Kolmogorov complexity defines the amount of movement of the data, but also the representation of the problem. And as we know from state machine theory, that representation, the state of the computation, is what tells us how fast we can iterate through the state machine. And so I realized this is one step before the actual computation that people look at. But let me step a little bit further back here. So this is my favorite example of representation. I was just recently standing on the beach where Euclid was contemplating his thoughts and learned that it's not in Greece, but it was actually in Sicily. So that was a revelation for me. But at the same time, here you have Euclid's text in the middle. And I apologize, a bit small, but you can imagine what it's saying. It's talking about these triangles here. And that was the state of the art. There were scientists like here gathered in large rooms talking about how they're going to compute the triangle, the different edges, the angles between them. And they were debating the meaning of Euclid's text. And in fact, it was so complicated that they had to write commentaries around. So you have the thing around the edge, which is the commentary. These are people trying to explain what Euclid meant when he said one side needs to be squared and then the other side needs to be square. Right? And so finally, of course, today, we teach this to school children, which is, we tell them, well, it's A and B, and you just do A squared plus B squared, C squared, that's it, and then you're done. These are the sides of the triangle. And any child can get it. And the only difference here is that we've changed the representation. We have a way to represent the problem rather than in a long discussion on the meaning of what a side is, to just variables and operators between variables. And so that is all that changed from one to the other to completely kill the complexity of this computational problem. And so it just shows that the representation is really key. There is yet another big jump that I'm making here. How much is it?
We make a class
Sorry? Less than 3. Any other suggestions?
Depends on what number system you use actually, what the system is.
Okay. Yeah. So what's your guess? What would you say then? How much is it for you? Yes? I heard something.
408.
408, great. Yes, it is 408. It's actually a famous computation. You can get a Nobel Prize for this. Unfortunately, somebody already got it, so that's gone. This 17 times 24 is from Daniel Kahneman. It's Nobel Prize in economics in 2002. So we're a bit too late. And it is true, in fact, that it is 408. It's completely correct. However, you need to engage system 2 in order to do this. So what Kahneman does, he's a psychologist. He thinks about the brain and how it's thinking. How do you think about things? And the book he wrote here is to explain to dummies like me what it is that he's done in order to get the Nobel Prize. It's a brilliant book. It's really, really nice. It explains thinking fast and slow. And so I was reading this and saying, okay, so the brain has things, he calls them system 1 and system 2. These are the names that he has given these two things. So system 1, system 2. System 1 is fast. It does quick answers. Like the answers of, well, it depends on the number representation, or less than 3. So it gives a quick response to the particular question. And then in order to actually get the answer, you gotta engage system 2. You gotta sit there and put energy in and actually do the computation in your head. I just recently gave a lecture with the same content. And there were handouts. And so we handed out all the handouts. And so everybody had this in their handouts in front of them. And so some people have looked ahead. So I asked the same question, how much is this? And immediately the first guy says, 408. Right? He's proud of himself, he's beaming out of happiness. The only thing is I changed the numbers. So the handouts has different numbers from up here. And so system 1 kicks in and proudly announces what the answer is. He's already looked ahead to the next page, he knows. It just shows that system 1 is hard to control. You cannot actually control system 1 doing things for you. It's like recognizing the text here. You cannot decide if you want to read or don't want to read this text. Because you're staring at it, you get to read it. Your brain will read it for you. You will know what it is, if it's a language you know and if you're used to reading. System 2 is hard. You got to actually put energy in. You got to actually want to do this. You go in your head and then do all the computations. And so you may already slowly catch on to where I'm going with this. If there is a system that has evolved over time, which does computation, which does thinking, with a fast and a slow system, there's an analogy there with what John von Neumann wrote. So this is the other thing that came to my mind when I was looking at this. And this is the original text from what he was writing there. And it's quite impressive. It says, we are forced to recognize. It's not that he's happy to recognize, or that he's excited to recognize, or that he's just recognizing it. No, no, no. He's forced to recognize what has caused the computer architecture community many, many decades of headaches, which is the possibility of constructing a hierarchy of memories, each of which has greater capacity than the preceding one, but which is less quickly accessible. So now memory works the same way. In order to compute, you've got to remember something, and you've got to compute. Okay? One is useless without the other, really. So if memories are small and fast, and large and slow, and thinking can be fast for small tasks, very slow for large tasks, we could actually put these two things together. So here is some work that we were doing on just computing a function. The simplest computation is a single input, single output, and well, that's a mathematical function. So things like sine, cosine, tangents, just to give us a few examples. Of course, there are lots of other very exciting functions out there. And the question is, what is the optimal way? Not what is a good way, but what is the optimal way to compute this using thinking and remembering? And we know, well, there is this thing, as the memory gets bigger, it gets slower, and as the computation gets bigger, it causes trouble. And so this nicely breaks down into the polynomial that you use to approximate something, and the table that you use in order to store it. So you can just store the whole computation in the table, just remember it. Or you can compute the whole thing using arithmetic. And of course, the optimal way to do this lies somewhere in between, where you have some amount of tables and some amount of polynomials, and then the question is, how big tables do you need to store coefficients? How many bits of the function do you want to split over? And what kind of arithmetic do you want to do? So that drives a whole load of approximation concepts that people have developed over the years, most of which actually missed out on the issue of discretization of value. So none of these approximation methods recognize that the numbers that they're dealing with are not infinitely precise. They're all assuming that there's infinite precision in your computation. This is the optimal polynomial. There's methods to find that. Given the discretization of value, all of that work can be redone. And so that's a beautiful topic for another 1,000 PhD theses, because you have to redo all the math of the last 100 years, now with actual discrete values. So what that really means is that the underlying hardware and technology changes the optimum, changes the place where you get the most out of it. Then you say, well, that's probably just a few percent. Nobody cares because you're discretizing from infinity to down to a fairly large number. Double precision floating point or quad precision floating point ought to be enough for everybody, right? That should be fine. At the same time, we'll see that the potential here is really a lot larger. In any case, I've done this in the brute force. I've said, well, okay, let's figure out what the optimum actually is. And so we ran brute force experiments where on the bottom you see precision, how many bits you use in order to keep the precision of your computation. And on the left you see range. So this is the number of bits that we use in order to represent the range of our numbers. And inside here you have functions like sine, log, and square root, and you have method. So TP2 means there's a table and a polynomial of degree 2. And then you see up there it goes to TP3, TP4. Over here PO is just polynomial only. It doesn't pay off to actually store any of the coefficients. And of course I ran out of energy at some point towards the right there. To keep doing this brute force, but it just makes the point that it is possible to find the optimum in terms of latency and throughput for these things. So let's step back and tackle the original challenge that we had in the beginning, which is to do computations as fast as possible. And I don't mean sine and cosine, I don't mean plus or minus. What I mean is to predict the weather. Because if you do your weather prediction and you take too long, actually it's worthless, right? Because if the weather already happened, you can go out there, just look and see, well, that's great, the sun is shining. I don't need the weather report to be telling me that. What I want to know is if the weather is going to be tomorrow. If I can't compute that by tomorrow, that's useless. And so you have a hard deadline for that computation. And a lot of computations like that have hard deadlines. And so what you have to do is to look at the entire space, which is again very uncomfortable because nobody likes to do that. People like to stay within their little field of expertise and just look at one tiny little sliver, maybe a compiler, maybe the architect, maybe the microarchitecture, maybe the computer arithmetic piece. But it is fairly unattractive to have to look at the method of computation. How does the finite difference grid approximate the world? Do you do the same thing in X and Y as you do in Z, or do you want to do a layered model? How does air flow up and down, left and right in space in order to predict the weather? How do you iterate in time as you compute that model in order to simulate how that weather is going to project forward? What is your discretization now? Discretization in space, discretization in time. On top of that, thinking about discretization of value, also highly unattractive. That has to, of course, interact and be turned as a machine in parallel to another machine, which is a bit-level representation, storage, and processors that are computing on all of this. And so if you wanted to claim that you have optimized the computation, if you optimize the system to compute the weather as fast as possible, clearly you would have to do both of these things all at the same time. And so here is a graph of a computation. This is a finite difference stencil for a 3D finite difference, which means that you're iterating in space and time by doing all of these computations. And this is an example of one of the things that we are doing, where you push the computation into the nodes, which are basically here arithmetic units, and you need about 5,000 of them. And then you can simply iterate in time by pushing the wave fields up on the top, and these are wave fields like velocity and actually density of the Earth for this particular example, and pushing them through to do one time step. And so as you iterate through this whole computation, you're actually simulating a physical system for them. So I like this guy because when he set out in the morning, he told his buddies that, oh, you know, I'm going to be taking my car, put it on the bicycle, and going to go across town, I'll put it on the other side. I said, no, you're all wrong. No, you can't do that. We don't do this. We don't take cars, put them on bicycles. He said, well, yeah, I'm just going to do it anyway. So here's an example which typically gets people to be really upset. At the same time, all it is a simple measurement that the Italian oil company E&I has done. And then they've published it, and apparently that is really bad. But what it says is that they've run this computation, and if you look at the various hertz, these are not frequencies for computation; these are frequencies in space. So these are basically how many dots they have in an image. For the 70 hertz peak frequency, what you get is an image that is 3D. 3,000 by 3,000 by 3,000. So you're talking about 27 gigabytes of data right there, maybe multiplied with a few bytes depending on how many you use to set numbers. And what it says is that 8 of the data flow cards that they were using, where each card is maybe this big and uses 50 watts of power, have replaced in their data center, go up there, 1,900 Intel CPU cores. right? So it's equivalent compute. They said, no, use this number of cores to compute this thing. It takes this much time. You know, compute it in the same amount of time. Oh, well, you know, we can now do it for this. So if you look at the power consumption, 100 kilowatts of Intel cores go down to 1 kilowatt. So clearly a lot of different types of optimizations have gone into this. And it's not just one little method here and there. But it just shows that this is a worthwhile activity. Maybe it does pay off to consider optimizing across all of the different levels of abstraction, putting all of these different optimizations together and trying to solve things as fast as possible. Here's another example where people say that sparse matrix computations cannot be parallelized. It's a real big problem because you have an iteration. Oh, no, the latency of that iteration defines how long it takes to solve your sparse matrix. If your sparse matrix is 1 million by 1 million, well, that's a lot of data. Even if it is sparse, you still need to move it out. And so this is another paper that was presented by a company called Schlumberger. It was presented at Hot Chips at Stanford. That was in 2010. And it shows that they have this product here on the left, which is a commercial geomechanics application. It does movement of rocks as you suck out the oil from a reservoir. The rocks start to move. There's not too much excitement about talking about which rocks move and how many earthquakes get generated by doing this. But they have this software that calculates how the rocks are moving. And it's a sparse matrix, finite element computation, of course. You can see the best scaling that they get using a 1 core, 2 cores, 4 cores, 6 cores, 8 cores, 12 cores. Well, 6, 8, 12 is already the same time. It doesn't go any faster. So it doesn't really parallelize on the large system. And you can get it to run about 3 times faster. And by reconsidering the encoding of the problem, reconsidering how we are storing the entire computation inside of a data flow appliance, you can see here on the right that we are running at between 20 and 50 times the speed of the Intel cores. So again, it does pay off. Now here we're not talking about doing something faster, we're talking about doing something that can otherwise not be done at all. And so that's where it gets really exciting, where you say there's not an advantage of maximum performance where you compute a bit faster than somebody else. Really it's about doing something that nobody else can do, regardless of how much technology they throw at it. Here's another example. Again, you can imagine there is not one single optimization that has led to this. But this was published by JP Morgan. Again, this is all the same computations. We're solving partial differential equations. They've reported that their computation time went down from 8 hours down to 2 minutes. And so that, of course, required a lot of optimizations of how the data was moving around in the system. But at the end of the day, it changes how much you can do. It also changes what you can do. Rather than running it overnight, you can now run it during the day. So hurry up a bit. There's a lot of examples of these types of applications. Getting back to system 1 and system 2, how do we actually implement this? And so that brings us back to the most efficient way of creating large amounts of anything. Right? So if you look at the Ford model of manufacturing, and you think we could do the same thing inside of a computer, rather than creating one result at a time, we could manufacture our results. And I'll leave it at this. There's of course a lot more discussion that can be done here, but just to show how that looks like. So the manufacturing revolution quite a while ago was not that pleasant for everybody. If you know the movie, you know how it continues. The poor guy doesn't really like it a lot. At the same time, it is a lot more efficient to have a system where you do things one thing at a time, and you have a thing where you manufacture things in very large pipelines. And of course, you know that the connection here is with talking about going from a pipeline of 20 deep to a pipeline of 20,000 stages. And by having enough stages, you can manufacture at a certain rate. You can control the materials going in, the products going out. You can now schedule your entire thing up front. And you can, in fact, get to something that is very nice, which is you can predict the timing of all the activities. You know exactly how much stuff comes out on the other side. And so if you care about how much time a certain computational task takes, that is, again, a very nice method to do this. So in fact, there is products around this that we have at this point. I'm not going to spend too much time on this, but just to show, there was a talk yesterday which nicely encapsulated splitting between data flow type and control flow type computations, and the idea here is to do it through an infinite network. There's a whole range of machines that are out there being used by, there's a small number of people who care about computing as fast as they possibly could, and networking related clients, and pure data flow clients, and then a combination of control flow and data flow. And so just to end with the programming model, which may be an opportunity for discussions after this talk as well, is that what we have is a Java-based interface that allows us to do Fortran, C, C++, any kind of scientific codes, and deal with hundreds of thousands of lines of source code that people have developed, so large amounts of legacy code, not just little toy problems, and put these things all the way from tinkering all the way over into production. The programming model, where you have a loop here on the left, where you're just computing, you can translate that into the actual expressions of the computation. You try to compute, you define your inputs, you define your output, you compile the whole thing, you get a data flow graph out, as you can imagine. You have to now tell the system how the data needs to move, so you have explicit data movement descriptions. When we move the X into the data flow architecture, X the counter, you say there's memory up there. In fact, there's a lot of memory up there. One of the key things is to have an adequate amount of memory. So what we do is we put 400 gigabytes of memory inside of a single one-use server to be able to hold sufficient amounts of data. And so finally, since I'm out of time, just to show how this technology is moving forward. So if you look at how many multiplications you can do per cubic foot, which is kind of one way of looking at the metric. We started off in 2008 with a product that had 400 multipliers in the one group. We went to 4,000, 8,000, 12,000, 16,000. We're going to go from Q2 this year to Q4. We're going to double the amount of computation we have. And so you can see an acceleration of the amount of things that can be done here, which is, of course, a combination of micro and macro architectural improvements across the whole system, but it just shows that the amount of computation is growing very fast. The limit is really getting the data in and out of that system, and so that's what I hope that we could get out of this. Thank you.
And maybe time for one or two quick questions.
When you look at Exascale challenges and to the power of 18 operations per second, then I guess the clock rate is limited, so we have gigahertz type, so the other 10 to the power of 9 you have to realize by maybe 1,000 nodes, and that means also that you still have to realize a parallelism degree of 1,000 per node.
Yes.
And if you look at PDE solvers and so on, the types of operations are exactly that. You have to do little computation, typically with stencil operations, and so there's exactly the problem of data movement. So How is the solution to this?
Well, the idea is that instead of having a lot of parallel actors who have to all do something and talk to each other and spend all of our brain power thinking about how 1,000 people could all make a car in parallel, you could think about creating a production line, having 1,000 dummies, telling them, you screw on the window, you put on the tire, you put on the paint. They don't even have to know what a car is. They don't have to talk to each other. They don't have to do anything with each other. You're moving the car through, rather than having the idea of communicating sequential, brilliant geniuses who are, the best they can be in making a car. Right? If you need 1,000 people, all being experts in making a whole car, it doesn't scale. You cannot find another 1,000 because you have to teach them how to make the whole car. It takes forever, right? So it's the manufacturing principle. If you want to scale something, we've learned how to scale things in the last 200 years. We just have to move the same principles over. And it's not that we haven't tried to do that. There is a lot of research in computer architecture that this is building on. And so I didn't have time to mention all of this. But it's just one way of computing scales up, and the other one does not. That's all it is.
Okay. Another question?
So how do you deal with the lint one? Sorry to ask.
Yes. Well, we don't. So lint-pack is it's basically a way to measure the guy who makes the whole car. We don't want that guy in the first place, let alone the way that the people figured out how to measure his performance. Right? The way you measure the performance of the guy who makes the whole car is you have to test him on the car. Right? So you give him a little toy car, and you tell him, put this car together. Right? So you take the little toy car, you put it into pieces, and give it to him and say, put it together again. You take the time and say, oh, that was very quick. You know how to put together a little car, well, the let you put together the real thing. Of course, I'm not going to take that little toy car and let a factory worker put together a toy car if all I want him to do is, I want him to put the wheel on the car. Right? That's all I want him to do. And then the next guy, I'm going to teach how to play with the paint. And that's really a different, because the activity is so different, the way to measure it and the way to evaluate it changes as well.
Okay. I think you will be still around, right? Oskar?
I'm around.
Yeah, okay. So then if you have more questions, you can ask Oskar offline. Let's thank Oskar again for the talk.
Then I was a break, and I think